Okay, so we've talked about the schedule and everything, right? All the homework is due by Monday before the exam. We have one last super session tonight, right? So go to the super session, get all your last questions answered, get everything clarified. Okay, let's quiet down. So we're ready on Monday. How many people went to this review session last night? Quite a few. Was it helpful? Hopefully. Okay. All right. Mostly what we have to do now is just do a little bit of practicing. So we've learned all of the reactions that we need to for this exam. And so we're just going to use some synthesis as a way to practice all of our reactions. Okay? Well, in addition to that, I can just answer some questions too if you guys have any pressing questions that you'd like to have answered before we go forward too. Nobody? I guess everything is just crystal clear. Yeah. You're so overwhelmed you don't even know what to ask. Yeah. I know. I always think about this time of the course. You think way back, when you were learning like substitution reactions or something like that. You're like, oh, we got SN1, we got SN2, we got two different reactions we got to learn, and you did addition reactions. Oh, there's at least 6 or 7 reactions. Oh my God, it's so many. How could I ever remember all of these? Right? Little did you know. All right, so let's do a clicker then. In the notes that I had posted, there was this one kind of synthesis, kind of 3 synthesis problems all in one. Okay, and so what I'm going to do, I'm actually going to do these as 3 different ones. We're never going to have enough room on one page, so we'll do the first one on the first page here, and then I'll have some new pages to do the other 2. All right, so in all of these, we're essentially starting with ethylbenzene. Right? We could just as well be starting with benzene itself, right? We know how to put the ethyl group on the benzene. And we want to extend a chain in these various ways. Okay? So let's first take a look at this one right here. Okay? So what we want to do is attach this ester here to that position, the benzylic position. How can we do that? Yeah, that might be a good thing. So first thing we need to do is we need to get a functional group at the benzylic position, right? And the one reaction that we know how to do at the benzylic position is to brominate it, okay? So we could go from here. What can we use to brominate at the benzylic position? Right, we can just use Br2 with, right, like light or heat. Okay, what else? Thank you. What else can we use to do that bromination? We can use NBS, the N-bromose succinimide. And this took like some H-nu or something like that. So this is an OR. Okay, so we've got a functional group at the benzylic position. How do we turn that bromine into an ester? We could form an alcohol, right? So we could what would we use to form an alcohol? We could use a strong base, like, so what do you want? You want to go directly to the alcohol, or? Okay. What would we use to do that? Well, yeah, we could probably use just hydroxide, right? Would essentially do an SN2 substitution, right? Or we could probably use just water and heat too. So this would be an SN2 substitution. Because it's at the benzylic position, we could probably do this as an SN1 substitution as well. Okay? All right, so we substitute that bromine for an alcohol. And then how do we make the ester out of the alcohol?
You could just use like a transesterification. Just have like another ester react.
You could maybe use another ester, or I think the thing that I would be worried about under acidic conditions here is you might do a dehydration. Because the double bond next to the benzene ring would be pretty stable because it would be conjugated. So maybe the best way here is just to use something like an acid chloride. Okay, and then we usually add pyridine in for these. Okay, just to absorb or to neutralize the hydrochloric acid that gets formed. All right, so we're, in theory we could use, an anhydride, we could use we might be able to use a carboxylic acid to do the Fischer esterification, we might be able to do an ester to do a trans-esterification, but we might as well, if we have those choices, we use the most reactive one here. Okay? So how else could we do this? Do we have to go through the alcohol? No?
I don't think so. I don't know how else.
You have this fuzzy feeling that you don't really have to do that because I asked that question, but you don't know how. Anybody? Yeah.
Did you make a ketone on the benzyl position?
Well, we could make a ketone here, right, at this position. Well, we'd essentially have to go to get to from ethyl benzene. We'd essentially have to go this direction, right, and then oxidize that ketone. We could do that, but I'm not sure if that gets us any closer to the product. Okay, because we have to have, that would be oxidizing this position at the benzylic position, which we don't really want. Okay, what I'm kind of getting at is that we could probably go directly from the bromine just by, and using this carboxylate anion, we could just do a direct SN2 substitution. Okay? So that's just using, that nucleophile and just going directly to the ester in that way. So in the end run, we're just making that a different bond in the final step, right? The carbon-oxygen bond instead of the oxygen-carbonyl bond. Okay? It makes it one step faster. All right, anything else here? Any questions on that? All right, let's look at the next one then. Look at the next one. Instead of at the benzylic position, we want to do the reaction out at the second position. All right, so we want to do the reaction over here. All right, so can we just brominate there and do our chemistry? Anybody? Huh? We can just use BR2 and HNU, and even though it's totally selective for the more highly substituted position, we can just hope that we get like 0.1% of the primary position. Yeah, that's a good strategy. Okay, so I think we really only have one way to functionalize the benzylic position. Okay, we can really, or even that side chain. Well, unless we want to oxidize the whole thing off, right? So we could do that as well. You know, we could use potassium permanganate. And this would go to the carboxylic acid. You know, that is one way to get a functional group on that side chain, but then we need to be able to add another carbon before we can, you know. So it seems like it's going a little bit backwards because we're losing one of the carbons that we actually need. All right, so what if we start the same way as we did before, and we brominate at the benzylic position? Okay, from here, what we really need to be able to do is move our functional group out to the primary, out to the end, right? The primary position. Yeah.
Could you do an elimination and then a hydrogen oxidation?
Right, we could do an elimination to form a double bond, and then the double bond is now bridging those two positions. And then we need to do a reaction that can then move the functional group out to the less substituted side. Okay, so if we do an elimination, we just use like, maybe we want to use a bulky base like tert butoxide so we don't get just substitution. And we can form a double bond out here. All right, and then we essentially have two reactions that are possible to put a functional group on the less substituted end of the double bond, right? One was suggested was the hydroboration oxidation. Remember that old reaction. Right, and remember this is just a hydration reaction, but the key thing about it is it does it in a anti-Markovnikov. It puts the OH at the less substituted position. Puts our OH out here. And then just like last time, we could just form the ester, and maybe the easiest way is just to use this acid chloride then. And pyridine. Okay, what's another reaction though that we can put a functional group out on the end of that chain from the alkene? Well, Br2, right, we'd put two bromines on. We just want one, say, bromine, but we want it out on the end. Yeah.
Is that when you use peroxide?
Yeah, exactly. So we can use HBr and peroxide. Remember, that's the radical addition. And it also does kind of what we could call anti-Markovnikov addition. So the bromine goes to the end. And then we could just use like our other approach, and we'll just use like this carboxylate anion as a nucleophile. Just do an SN2, get a primary position. We can easily do an SN2 substitution. Okay? Any other ideas or questions, comments? No? All right, let's look at the third. Down to one slide, huh? That was dumb. And even I'm an expert at packing it in. Okay, so let's look at this one. Okay, so in this case, we want to do a reaction probably at the benzylic position, but we need to add this whole piece right here. Okay, so we want to add 2 carbons and then an oxygen at the benzylic position. Okay, so we're kind of stuck with the same first reaction. Okay, so let's just brominate at the benzylic position. I'm going to draw it like this just to show how maybe it's related. Like this. Okay, so if I was thinking about this, I would think about it in kind of 2 steps. You know, we have 2 pieces we need to add. We've got this piece right here eventually, and we have this piece right here, right? So we're probably going to have to add 1 piece and then another. Or we could add the first one in, you know, we could, if we wanted to run this out, we could add 1 carbon and then another carbon and then an oxygen and an ester and stuff. So let's work backwards here. Let's say we know that we can form that ester, right, from an alcohol. From here, right? And we know that we can use, like we did on both of those last ones, one option was to use the acyl chloride, acetyl chloride, and pyridine. Okay, so how do we get from here to here?
Can we make it to a Grignard?
We can make it to a Grignard.
Make it go into the carboxylic acid?
We could make it to the carboxylic acid. So I'm going to run it down here because this is going to take a few more steps. So you mean, so you want to, what do you want to react the Grignard with to make the carboxylic acid? CO2. 3, we've got to add some acid in the end. Okay, so we've extended that position 1 carbon. So now we've got to add another carbon as well. Is there a way that we can add both of the carbons at the same time? Let's say we're going to make the Grignard. What can we react with the Grignard to add 2 carbons and make a primary alcohol? Come on, somebody can remember this, right? Well, an aldehyde we could react it with, but it's going to, right, if we react this with an aldehyde, it's going to make the alcohol at, come on here, this position over here. An epoxide, good. Right? Hang. An epoxide, oops, 3, add some water or some dilute acid in the end. Right? That Grignard attacks the epoxide, opens up the ring. We protonate, makes the primary alcohol. Oops, I could have just gone right up to that other one. All right, this is the same as that. Yeah.
And just to clarify that, it doesn't matter in this case, but it'll attack the epoxide in the least substitution?
Correct. So if our then the Grignard, being a very basic reagent, will attack at the least hindered side, the least substituted side. So when we have basic reactions, basic nucleophiles, they tend to act at the most exposed position. So it's more of a kinetically controlled one. It just goes into wherever it can access it most easily, right? If it's under acidic conditions, then it comes in at the more substituted position, because that's the position that can hold more of a plus charge. Okay, so maybe we should, anything else on this one? All right, let's. These are all looking kind of the same, but let's. I just putting that benzene ring on each one of these. Oops. Take a minute and see if you can come up with some kind of strategy here. Doing here? Oh, that's to there. This one's gonna have a few more steps in it.
Oh, wait, no, sorry. What did I?
Well, not that many.
I think I could use.
All right, so any ideas? Okay, so let's think backwards from the end. There's multiple ways to do this one. Okay? So one way we could do it would be not in one step here, but would be to essentially make this bond right here. Okay? And the way that I would think about doing that, this would take us 2 steps to do, but if we could have, say, a Grignard here, oops, we could react that with, say, an aldehyde over here. Okay, would that go directly to that product? It would make an alcohol. Good. Okay, this is what I said to some of you, like when I was first showing you this, is that even though I went over this, I thought I went over this reaction a million times, probably some of you will try to do exactly that in one step. Okay, just warning you. But this is not going to go in one step. When this Grignard attacks over here, right, these electrons are going to go up onto the oxygen, and then we protonate that, right? So a Grignard with an aldehyde always gives us an alcohol, right? So we're going to get to here, right? And then how do we convert that alcohol into the ketone? Right, we just need to oxidize it, all right? So we can use something like PCC, or we could use some, well, chromic acid might be too strong. Chromic acid, like potassium permanganate, can also oxidize it off at the benzylic position. Okay, so it's, and I think in general, if you have choices, it's oftentimes better to use the more mild reagent if that will get by than to use something that's super harsh. Okay, so PCC will oxidize a secondary alcohol to a ketone. Okay? All right, so we've got the last part of this. What we now need to do is get from the benzene over to this Grignard. All right, so clearly we're going to make that Grignard from a bromide, right? If it's the magnesium bromide. Like this. Right, so how do we get to benzene, from benzene to that bromo compound? Bromopropene. And one bromopropane reacting with benzene? Is that what you mean? Okay. So if we do this,
Electrophilic aromatic substitution.
right, so it would be a Friedel-Crafts, right?
Yeah.
Is that, okay, this with what would our, we usually use, or oftentimes we use the chloride, but we use like aluminum trichloride or something as the catalyst. Does that give us propylbenzene? No, it gives us isopropylbenzene.
Yeah, that's right.
Damn.
Because the hydride.
Right? Because it can do a hydride shift.
So you can get it like OH there.
So close. Yeah.
Is this where we do like an acylation? Then
Right, you could do an acylation. So we could use the acid chloride and aluminum trichloride. Goes to here. Oops, except for this is a benzene. And then we need to reduce that thing off, right? So we can use, remember there was like that Wolf Kishner and that Clemenson and all those cool ones. One was like zinc amalgam. Remember that story when I made the sodium amalgam and I broke my flask and all that stuff? And HCl. Okay, so we got to here, then we can brominate there with NBS. Okay, any other ideas? How about this one? What if we went to the just bromobenzene? Okay, and what I'm going to do is I'm going to add all of those carbons at the same time. All right, but I'm going to limit us. So the problems on the exam, the synthesis will probably limit the number of carbons you can add at one time, at least in one reagent. Okay, so maybe 2 or 3 carbons at a time. Right, so if I want to add that whole carbon skeleton thing here, so if I want to add all of these carbons in one reaction, let's think, what did I do here? I didn't quite do that right. I'd have to add one more carbon. Well, let's just follow this out. So we can we can always, so from a bromine like this, we can make a Grignard from this as well. Okay? So then, I'm going to cheat and I'm going to do this all, I'm going to say, oh, in this problem, because I'm making this one up and this isn't on the exam, in this one you can add 5 carbons at once. In the exam you can't do that. So what can we add to this Grignard to add 5 carbons and a branch thing like that? I'm just going to add this ketone. Oh yeah. Okay. When we do that, it's going to add this, and we're going to have an alcohol at this position. All right, so now the question is, how could we possibly get from this alcohol down here up to this one over here? How could we move the alcohol from this highly substituted, huh?
Can we do a dehydration?
We could do a dehydration reaction. That's right. So we could do a dehydration reaction, right? So we could use something like some sulfuric acid or something like that. We lose water. Both of those alkyl groups are the same, so it doesn't matter which one we lose it from. And we go to something like this. Right? And then we do our hydroboration oxidation. OH minus goes up to there, and then we can do our oxidation. Okay, so just what I was thinking about before is there another thing that you could make this alkene from rather than the alcohol? Yeah? What? The Wittig, right? So we could also make that from this ketone with the Wittig reagent. Okay, remember that has phosphorus and these three phenylphosphines, and we want to add 2 carbons, right? So we're going to be adding both of these carbons right here. And so our ylide would look like this with a double bond and another methyl group there. Okay? And so remember what happens in this reaction, right, is essentially the oxygen, we take the oxygen off, we take the phosphorus off, and we just connect those 2 double bonds together into a single double bond. Right? And then if we did it that way, how could we make this ketone from benzene? We already did. Look at that. Right? We just did the acylation to here. We do the Wittig, hydroboration oxidation, esterification. Right? And we could probably come up with, 5 more ways to do this. Right? Wouldn't that be fun? No. Yeah, question. Acylate the whole thing. You mean to alkylate? No, not really. No, we can't really put that whole thing on at once. Yeah, so that's the tendency you gotta be careful of when you're doing these syntheses is don't try to go for the home run swing all at once, right? If you put everything on at once, then it's probably gonna be wrong. Okay, you gotta do it kind of stepwise. All right, let's see if I have anything else on here. 5 out of 5. Okay, let's do something, we have just a few more minutes here. Which one of these do I want to do? Which is the coolest one? Let's say we start here and we want to go to this ketone here. Yeah.
Are you gonna explicitly state on the exam, like synthesis question, like on this question you can only add at maximum 3 carbons at a time?
Yes, absolutely. The questions are stated just like that.
Okay.
Yes. Everybody hear that? So the questions are, you can goes from here to here, and you can use any reagents that we've learned. I'm not giving you a list. You can use any reagents you want that you've learned in last semester or this semester, and you can add up to a 2 or a 3 carbon piece at once. Yep. I know, I make you remember all those things. My theory is there, if I just give you a list, then you don't really learn it as well, and you just think you're going to go into the exam and look at the list and figure it out by what's available. Right? It's like going into your physics exam with a list of equations. You don't need to know what you're doing. You just go and find the equation that has the correct variables. All right? Exactly. That's a much better way to do it, isn't it? Okay, so what we're going to do here, there's also multiple ways to do this one, but we're running out of time here. Essentially, we're going to need to make this bond right there. And so we're going to first go to a bromine. So we're going to add a bromine to the end. We're going to use HBr and peroxide. Okay, and we're going to get to here. And so there's more than one way to then add the other. In this case, we're going to add, well, one way would be involving adding 3 carbons. One would be adding 2 or less. Okay, let's say if we can only add a maximum of 2 carbons at a time. How can we do this?
It would have worked if it was 3.
Right, I know which way that is. Okay, this one you probably don't remember, though we just covered the other day. What if we used cyanide? Right, and we make this nitrile. Can we go from the nitrile to the ketone? We can? How do we do that? We could do it a number of ways. The most direct, remember, is that if we use a Grignard, see, Cl, like an ethyl Grignard followed by water and probably a little bit of acid. Remember, we went over that the Grignard will attack the carbonyl and essentially go to an imine. Okay, so it goes through an intermediate that looks like this. So it's an imine. And then under acid and water, this gets hydrolyzed to the ketone. Okay, that was the very last reaction that we learned for nitriles. Okay, another way to do it would be to first reduce it with dibal, followed by water, and I think better with a little acid in there. What does that give us? An aldehyde. And then how do we get from an aldehyde to the ketone?
Oh, should we just use like another, thing here?
Yeah, so we could use another Grignard. Would it go directly to the...
No, make it to an alcohol.
Okay, I'm going to do this all in one here. We're going to add a Grignard. So we want to add an ethyl. So like that. Then we have to add water to quench our Grignard. And then what would we have to do as a separate reaction after that? We have to oxidize again, PCC. Right? We could also hydrolyze this to the carboxylic acid. Right? We could, here, let's do that. Are we out of time? Dang. This is so fun, though. We could go to the carboxylic acid, then we could go to the acid chloride, and then we could use a cuprate to go directly to the ketone. All right? Okay, so what?